And we are recording.
Hello, everyone. Welcome to another session of Book Club. Yeah, we're actually doing Karuta, but we finished L2 and we're going into L3, so we need to read more of the book. So that's
Yeah,
what
and
we're
we're
doing.
gonna try to do it as we go. That may not pay off, but well, we have evidence that worked before, so let's try.
All right, so the language L3 corresponds to pure prologue, as it extends the language L2 to allow disjunctive definitions. In other words, or. We already have and. It's a set of procedure definitions. A definition is an ordered sequence of clauses. Yeah, that's basically the same. Queries are the same. Semantics operates using top-down leftmost resolution, an approximation of SLD resolution. Um, thus, in L3, a failure of unification no longer yields irrevocable abortion of execution, but considers alternative choices of clauses in the order in which they appear in definitions. Yeah, so this is basically
This is what's going. This is what's going to make it to incomplete then.
yeah, this is basically depth first search essentially.
Yep.
And this is done by chronological backtracking. The latest choice at the moment of failure is re-examined first. Yeah. So we need to change the design of the machine M2 to save the state of computation at each procedure call, offering alternatives to restore upon backtracking to this point of choice.
Damn.
That's called the choice point. Uh, Actually, I'm kind of wondering. We don't.
We don't save anything.
Yeah, we're not saving really much of anything on the stack at the moment when we do a call instruction. I wonder
Yeah,
if
yeah,
that's
but
gonna get.
yeah, we're gonna save. Gonna have more stacks. I can already give you that hint.
Yeah. Uh, we need to analyze what information must be saved as a choice point in order to create a record, a choice point frame, where from, nice word by the way, a correct state of computation can be restored to offer another alternative, with all effects of the failed computation undone. Um, yeah, this is basically just backtracking. Choice point
Yeah,
frames
yeah,
must
but
be organized
focus
as a
that needs to
stack.
be pure though. We cannot undo side effects.
Well, yes, that's why it's saying it's a subset of pure prologue. Like it has no side effects, it only has failure and backtracking, essentially.
Nice.
No mutations. No mutations.
I wonder what we're gonna do when we introduce those.
Uh, well, the easy solution, and what I think most prologue implementations do if they have mutation is okay, backtracking keeps the mutations. Like that's just the easiest thing to implement.
But isn't that dangerous as fuck?
Is it?
Well, yeah, because I'm trying a path of execution and I mutated the shit out of everything. Ended up being wrong. I cannot undo the effects and I'm gonna try every other single available option with the mutations from the previous attempt. How is that not dangerous?
Well, mutation in general is dangerous. Um, so
Well,
yeah.
they are not dangerous if you can revert them.
Uh, well, yes, but that would imply implementing a notion of a state of the world, so to speak, that is transactional, essentially.
Yes,
There
agree on
is,
that.
I remember seeing a paper about a language that does that, but it was
Mhm,
not a
mhm.
logic language. It was actually a JavaScript variant, believe it or not.
Weird.
Yeah, I don't know why that choice was made, but that choice was made. So, uh, actually, I wonder if. Hmm, well, never mind.
Yeah,
I'll
let's
remember
continue.
that later. So choice points. To distinguish the two stacks, let's call the environment stack the end stack, and the choice point stack the or stack. Yeah, yeah. Um,
What?
actually, no, I actually skipped something, but yeah. Basically, we're implementing or. We already have the. Well, the call stack is not being used properly because we don't actually. Um, you don't actually push stuff onto the stack when we do a nested call because L2 doesn't do that. So But yeah, it's the end stack, and now we are adding or.
Should we stop the reading and add code now?
Uh, and it's organized as a linked list. Well, we could, but let's
Yeah,
see.
that's already a lot of code because now we need to change the store as well.
Uh, do we? Maybe we do.
Well, yes, because we only have the and stack. Well, actually, there is no the distinction of and or. We're gonna have to introduce those as well.
It's in the machine,
No,
right?
do a git checkout to main and pull, and then checkout to L3.
I'm already on master.
Did you pull?
Yes.
Okay,
See?
so checkout L3.
Uh, uppercase, because yes.
Sure.
Store. Stack size. I think we're actually going to use this segment for that.
What is this machine? No, no, no.
The
Yes, we're gonna
PDL, no,
also.
the PDL segment of the store. Because
Oh,
we haven't used it. Yeah, we haven't used this yet.
well, but that's not how that works, Marinho. It's not because something's not being used that we can reuse it at a glance. We need to understand: are we supposed to use the PDL for the order stack or not?
I mean, this is the only memory region that doesn't have a clear purpose because we made this based on that picture from the original paper, right? It's not from the book.
Well, in that case, we can continue reading because you already have operations for the PDL.
Uh, the head of this list always corresponds to the latest choice point and will be kept in a new global register B. Do we have that? We don't. Uh, such that upon failure, computation is made to resume from the states recovered from the choice point frame indicated by B. So yeah, basically a second stack register.
Let's introduce B then.
Mm. All right, so B register is an int.
And we need to change the initialization function at the bottom. Wait,
I don't think
if
0 is the right value though.
exactly, if is this a stack thing? So we should use store something.
Mm, let's
PDL start
assume,
maybe?
yeah, let's assume that it's the PDL uh, start.
Oh, there is
And
no
I don't
PDL start because it
think
starts on the bottom, right? It grows the reverse. Oh, it's trail start, 82.
trail starts. All right, all right. So trail starts.
It's still
Is
wrong.
this public? I don't think it is actually. We
So
need
go to
to
the
add it to
signature
the
and add
signature.
that. There it is. There it freaking is.
Uh, okay.
Unbound.
Unbound value.
Try to compile. Ignore LSP.
Classic. Karuta. Well,
Dune
not
Karuta
Karuta.
exec.
Dune Karuta exec. Um,
Exec Karuta maybe?
build.
No, I think we are doing it reverse.
It builds apparently.
Fuck LSP.
Yeah, the LSP for OCaml is questionable.
Yeah, you can remove the fix me though.
Uh, When the latest frame offers no more alternatives, it is popped off the OR stack by resetting B to its predecessor if one exists, otherwise computation fails terminally.
I have a question.
That, yes?
What is the B register holding? An address?
Well, it should point to a frame in this new stack that is being introduced here. So yes, it's an address.
But it's an address on the stack. Okay.
Clearly, if a definition contains only one clause, there is no need to create a choice point frame exactly as was the case in M2. For definitions with more than one alternative, a choice point frame is created by the first alternative and then it is updated as far as which alternative you try next by intermediate but non-ultimate alternatives. And finally, it is discarded by the last alternative.
Wait.
Basically, if you have a NOR, only if you see a NOR, you create a frame before you do the first alternative, and then you have to update the choice point um, after you fail each alternative, and if you reach the last alternative, before jumping into it, you have to
But
discard the frame,
okay, so this
essentially.
is doing short circuiting then.
Short circuiting, essentially, yes. If you have a failure, you're going to short circuit.
No, no, no. It's the opposite. If you have a success, instead of trying all the other options, you just go with it.
Yes.
Okay.
Uh, yeah, if a choice point. Well, no, actually, because
No, you
otherwise
may
that
fail
commit.
later, right? But no.
Yes, and you need to be able to backtrack if you fail later. This is not committed choice. This is normal choice.
No, 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 yes, but what I meant with short circuiting was just like, okay, I got a path that works. Instead of trying the other paths to see if they also work, I'm just gonna go for it. I'm only gonna go back if I ended up with a failure.
Yeah.
Okay. Okay, so now we are going to talk about the interactions between the two stacks.
As long as we consider deterministic L2 program definitions, it was clearly safe to deallocate an environment frame allocated to a rule after successfully falling off the end. Right, after you return, essentially.
Yeah.
Mm, yeah, later failure after you return may force you to go back, essentially. Yeah.
Yeah, makes sense.
And this is the example program that I give. Mm, A is B and C, B is E, C is 1, or it's a fact. E is either F or G, so there's a disjunction here.
Wait a moment. Um, what changes? Are we doing a failure if we encounter duplications?
Maybe we are currently. We need to change that,
Copy this
yes.
program. Let's put l3.karuta and see what happens.
Okay. Let me just.
I'm very curious because I don't think we are doing that actually.
Yeah, this is gonna be kind of messed up when I paste it, but okay. Um,
No, it happens.
examples L3 dot Kurt, and I need to do. That's not what I wanted, and of course that messes up. Uh, Here, Excel. Actually, that's just it.
Damn.
And yeah, this is messed up.
Okay, that was worse than I thought. That's cool.
Okay, A is B of X and C of X. Is that it? Yes, that's the correct order. And then, yeah, it's probably easier to just type it
Yeah.
out.
I can
B
actually help you with that though.
of
Let me pick the book
X
here.
is E of X Then C is a fact that's valid for 1.
Oh, we have numbers.
We were adding them in another branch.
No, we're gonna have to merge that then.
Maybe, yes.
Okay.
And
Uh,
then E of X
did we make it
holds.
work though, or is the branch work in progress?
I think it's a work in progress still, actually.
Okay, we're gonna have to replace the numbers with something else.
Like, we can parse the numbers, but I don't think we're using them yet in the evaluator
Yeah.
or the compiler.
Okay, I completely forgot about that, but okay. Okay, so these ones are EX, FX,
And
EX,
then
GX.
F of 2 and G of 1.
Yeah, we're gonna have to get rid of the numbers though. So what are we gonna
Oops.
do with the instead of numbers?
Actually, I think. Let me check the lexer. Um, yeah, lexer. Ident is a lower letter. It doesn't allow digits. Okay, so let's just replace the numbers with a, oh, x. This was 1, right? Let's
Yeah,
change it to x, lowercase. This is also
Y
x,
and
and this is y.
okay, that works. What happens now? I'm
Uh,
kind of nervous actually.
well, let's try to compile that. It's probably gonna break, but
36.
yeah.
Yeah, but I wonder where is going to break. It failed parsing. Awesome. I actually know why, I think. Go back to the program. I think line 1 doesn't work.
Oh, right.
I don't know if that's going to work better, but let's see.
It
Damn.
does.
Okay, but we don't know what happened though. It didn't fail, which means that we parsed, allocate, register allocated, code generated, and evolved.
Okay, let's just print the instructions then and see what's going on.
We are not checking for duplications. I'm kind of surprised actually. I was kind of certain we would be
Uh,
doing that, but I'm
yeah,
glad we
here.
didn't.
So it's not failing there, apparently.
No, it's not failing anywhere. The program works.
But it's
Uh,
not running because it's not actually. Oh, right, because we don't have a query. Of course, it's not gonna do anything.
I love when this happens. When it's not that our program is wrong, the program is right and we are in the wrong. But we made it.
Yeah, there we go. Unreachable get
Ooh.
structure.
Ooh. Okay, before that, let's go back. Let's see the code generated.
Uh,
No, it's
I
on the
don't think
bottom.
we're. No, we're not. Those are the instructions executed, actually.
No, okay, so never mind.
We're calling A, put variable, blah blah blah, calling B, then we're calling E, which is correct. Then we're calling get variable and put value using E. Uh,
Oh, this is also depth first then.
Actually, no, I think what's happening, we're calling G here, see? What's happening is when we emit the code for the second E here, when we generate the functor table, it's going to overwrite the address of the previous version of the E predicate.
Ah.
See?
Okay, so we did have, well, not a check for duplication, but the data structure is doing the some funkery.
Well, yes, it's a map, so if you overwrite the same key, it's going to lose the previous value.
What are we gonna do about that though? Are we gonna save multiple values on the value side for the same key?
No, we should probably do that desugaring pass that we were talking earlier
Man,
because
but that's not what the book is.
the
That's
book may give us a solution if we keep reading, though. So there's
Uh,
that.
okay, but at least we discovered what happens with L2 if you try to run this.
Yeah, it's going to try this because this happens after this. Well, with our implementation at least, right?
Mm-hmm.
Executing this query, which I added to the program, allocates an environment for A, then calls B, then an environment for B is allocated and E is called. This creates a choice point, which we don't have implemented yet. And an environment for E is pushed onto the end stack, and at this point, the two stacks will look like this.
This
Uh,
actually makes sense. The second E implementation goes on the second column, on the second stack, right? Marinho?
yeah, sorry.
No, no problem. The second E implement definition is going to go to the stack on the right. Is that correct?
This will add a choice point. Yeah, we need to say, okay, over here, there are these two possible bodies for this predicate. We need to register that somehow. But this is dynamic. This is after compilation. It doesn't tell us how to deal with the fact that E has two bodies yet.
Wait, repeat the last part.
This is explaining what happens at runtime. We haven't seen how the code gen for this looks like yet.
Ah, okay.
The following call to F succeeds, binding X to 2. Yeah, we're definitely not doing this because of how our functor table is implemented. Um, the environment is deallocated,
Wait,
then the
why
environment
is X going to 2? Oh,
because
it's because F is 2. Okay.
F holds for 2 only.
Okay, 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 okay.
And this
Wait,
will
but
lead to
why
the
that would not work with our stuff, though?
because because the way we implemented the functor table, we're going to call this every time.
Ah, okay, we're not gonna be able to do the unification. I see, I see, I see. Okay, let's go. I'm following. Okay, we
Then
deallocate
it
some
continues with
environments.
A.
Wait, the continuation follows up with execution of A's body, calling E, right?
C.
C. It's hard to see here. Which is gonna fail because X is true, and the only C fact is for 1. Okay, it's gonna fail. The choice point indicated by B shows an alternative clause for E, but at this point B's environment has been lost, which is our case. Indeed, in a more involved example where C proceeded deeper before falling, the old stack space for B's environment would have been overwritten by further calls in C's body. Therefore, to
Yep.
avoid this kind of misfortune, a setup must be found to prevent unrecoverable deallocation of environment frames whose creation chronologically precedes that any of the existing choice points. Yes, the idea. Uh,
Oh, I think this is going to create some kind of stack of stacks, essentially.
damn! Marinho's dream.
Ah, well, that's literally how continuations are implemented in Factor, actually. Except not a stack of stacks, it's a stack of a tuple of like I think it's 5 stacks that Factor has internally or something. It's a big stack, yeah.
Yeah, so the idea is that every choice point must protect from the allocation of environment frames already existing before creation. Now, since a stack reflects chronological order, it makes sense to use the same stack for both environments and choice points. A choice point
Oh,
now caps all other environments. Yeah, so this is what I said then.
so actually they will be kind of interleaved, I guess.
Wait, I don't know if I'm following. What are you thinking?
Well, it's saying right here, it makes sense to use the same stack for both environment and choice points.
Oh, so we're gonna actually generate code for both. Wait, we're gonna use the stack for both environments.
Yeah, the stack is going to have two types of frames, basically.
Which types?
Well, the environment that we already have and the choice point that's new.
Okay. Following it up. A choice point now caps all other environments. In fact, as long as it is active, it forces allocation for the environments on top of it, preventing the order environment stack space to be overwritten, even though they may be explicitly deallocated. Wait, what?
Yeah, so basically if you return, but there's a choice point between where you are and the environment that you're returning from, you're actually going to keep that frame because you can't
How are we going to
deallocate.
remember that though? Like,
That's a good question.
like how I'm going to know at the current point in time that, wait, I am in the middle of a choice point, I should not deallocate this actually.
Well, the choice point will be on the stack. It's gonna tell you that,
No,
but
but
I'm not sure.
no, we need to remember that for further execution. We allocate the choice point, fine. How are we going to know further on the line that
Well,
that has been
basically,
allocated?
the instruction that deallocates an environment frame, you need to check if there's a choice point above it, and if there is, it needs to do something different.
But that can go arbitrarily deep though. I think we need a boolean.
No,
Ironically.
we don't. It can go arbitrarily deep, yes.
Yeah, so
Why
it's
wouldn't
not
it?
necessarily the case that if you at that moment of the stack, at that point in space of the stack, if you look above you, there may not be a choice point upward, like above you, but above that there may be one. You see?
Well, if there is a choice point before, like above the, if you have an environment above a choice point and you deallocate the environment, that's fine. That's just returning without changing the, without going through the choice
No, man.
point,
No.
essentially.
Imagine two paths. So we have a choice point on the bifurcation. So one path you go 3 calls deep, and in the other one you go 5 calls deep. On the third one of the first path, when you reach a failure, how are you gonna know that you are in a choice point?
Well, the failure will have to unwind the stack until it hits a choice point.
Ah, okay. So you keep returning until a choice point is reached.
Yeah, it's kind of like, failure is kind of like throwing an exception, except you don't have an exception object
The
carrying
choice point is the
information.
catch.
Yeah, essentially.
Okay. This allows their safe resurrection if needed by coming back to an alternative from this choice point. Moreover, this protection lasts just as long as it needed, since as soon as the choice point disappears, all explicitly allocated environments can be safely overwritten. That makes sense.
Hmm.
Hence, there is no need to distinguish between the AND stack and the OR stack. Doo-doo-doo. Calling the single one the stack.
Amazing.
Choice point frames are stored in the stack along with environments, and thus B's values and address in the stack. Going back to our
Okay.
example above, the snapshot of the single stack at the same first instance look thus. Okay.
Okay, so we have an environment, we have another environment, we have a choice point, and then we have the environment after that.
And at the second instant as before, the stack is such that having pushed on it the choice point for E protects B's deallocated environment, which may
Which
still
may
be
still
needed
be
by
needed by
future
future
alternatives.
alternatives. Yeah.
Okay, so let me see if I understand. We go onto A, then we go into B, and when we go to E, we identify that there's a choice point because there's multiple choices, and we need to not deallocate B. We need to save it on the stack.
Yeah, we need to protect it from being deleted when we return.
Okay. Now the computation can safely recover the state from the choice point for E indicated by B, in which the saved environment to restore is the one current at the time of this choice point's creation. There is that the existing of still existing of B. Having no more alternative for E after the second one, this choice point is discarded from upon backtracking, which ends up safely ending the protection. Execution of the last alternative for E proceeds with the stack looking thus.
Yeah, basically, if you are at the last alternative, there's no choice point anymore. Because if you fail, you
No,
fail.
of course. Makes total sense. Okay, what's in a choice point? That's exciting. So
What's in a name?
when a chosen clause is attempted among those of a definition, it to create side effects on the stack and the heap by binding variables residing there. These effects must be undone when reconsidering the choice. A record must be kept of those variables, which need to be reset to unbound upon backtracking. Hence, we provide, along with the heap, the stack, and the code, and the PDL, a new and less data area called the trail. Okay, so we gotta go back to the code and add the trail.
Oh, we already saw the PDL before. Okay.
I have no recollection of that at all, but
I
okay.
don't either.
Yeah, but who? Well, let's undo what we did. We need to add the trail now.
Mm,
No, let's actually go first to the store and change the name because that name is wrong. Yeah, let's change trail start to PDL start.
okay.
Yeah, we need to change the signatures
Oh, that
above.
actually breaks.
Yeah, of course it breaks.
Oh, right, because of the signature. Oh, makes
Yeah,
sense.
and the signature of the layout as well.
Hmm.
Yeah, go to the layout signature above, all the way to the top on the top of the file. Let's change the trail PDL size to PDL size only, and let's add the trail size as well.
But the trail and the PDL, they grow in different directions. Like, if
Oh
you
damn.
remember,
Okay, you're
yeah,
right.
let's just go further a little bit. The trail is organized as an array of addresses of those variables which must be reset to unbound upon backtracking. It also works as a stack, and we need a new global register tr. I think we have that, right? Or not?
Where?
Yeah, we don't have a tr register. Okay.
Yeah, we're gonna have
Uh,
to add a new one.
okay, so tr register is the trail starts. What's the b register then? Oh, of course, that's actually the stack starts because there's only one stack.
Yeah. Yeah, but I need to introduce the TR register in the type definition. Nice.
That's after the s register, so yeah, whatever. Tr register int. Not all bindings need to be remembered in the trail, only conditional bindings do. That's one affecting a variable existing before the creation of the current choice point. So we use a new global register HB.
We do what we do best, buy more hardware.
to contain the value of age at the time of the latest choice point. And there's a footnote. Strictly speaking, this register can in fact be dispensed with, since as we see next, its value is that of age which will have been saved in the latest choice point frame. Okay. Let's add the register anyways.
Sure.
Uh,
And I forgot, what is the purpose of the H register again? Is that the one following the stack?
the age register, it points to the next free cell in the heap
Oh, okay.
where we will allocate new variables essentially.
Okay. It would be kind of nice if we had like a data sheet and of the book had a data sheet with the descriptions of everything of the machine. Because I keep forgetting because the names are terrible.
Well, yeah, the names are terrible actually.
The names.
uh, mm,
Let's continue.
all right, so
Uh,
hence only bindings of the heap, respectively stack, variables whose addresses are less than HB, respectively B, need to be recorded in the trail. Right, because we're using that trick where, well, the architecture is using that trick where, because you allocate everything in a sequence, right, you're kind of using things as stacks. If you have a choice point, then as long as you remember where the stack was before the choice point, then yeah, this gives you the necessary information. That makes sense. We shall write this operation, okay, is performed on store address A, and as mentioned before, it is done as part of the bind operation. Oh, right, this was that thing that until now was basically just setting a variable, and they said, oh, we're going to make this a function because we're going to change this later. I guess this is later now.
Wait, which function are we talking about? I don't remember bind.
Bind. Bind. It's do we have it? Yeah, we have it here, basically.
And what is this doing? This is grabbing an address, two addresses, and it is putting a reference, using one as a reference in the other.
Yeah.
Okay. Okay, let's go back to the book because I didn't read. So we shall write trail A when that operation is performed on store address A. As mentioned before, it is done as part of the bind operation. Okay. Let us now think about what constitutes a computation state to be saved in a choice point frame. Upon backtracking, the following information is needed. Um,
Argument registers, where n is the arity of the procedure offering alternative choices of definitions. So I guess we're not actually going to have a syntax for OR yet.
Maybe
But
never,
okay.
actually.
This is clearly needed as the argument registers loaded by put instructions with the values of arguments necessary for go being attempted are overwritten by, well, yes, we need to remember the arguments so we can go back and try again with a different body, I guess.
Yes, makes perfect sense. I have a question. What about
Okay.
introducing the syntax for OR now? Like, we're not using pipes in the parser. We can use pipes as like OR patterns in OCaml.
Traditionally, we use, well, Prolog uses semicolons for that, actually.
No, Erlang does the same.
Well, Erlang was written in Prolog originally.
No, that makes sense. No, my Git already complained about that multiple times. Uh,
Okay, so we need the registers, we need the current environment to recover as a protected environment as explained above. We need the continuation pointer as the current choice will override it.
Wait a moment though. Where are we saving all of those things?
Those are all registers.
Yes, but we are saving those on the stack.
We will need to save them on the stack when we create a choice point, yes.
Okay, so a choice point is basically dumping a lot of stuff.
It's basically dumping the current state of the machine onto the stack.
Okay. Okay.
The latest choice point were to backtrack in case all alternatives offered by the current choice point fail. Yes, this acts as the link connecting the choice points as a list. And it's reinstated as a value of the B register when we discard the choice point. Okay. The next clause to try in this definition in case the currently chosen one fails. This is updated at each backtracking to this choice point if more alternatives exist.
That's a little
Okay,
strange. I
Well,
thought we would
that's
save a list of them.
yeah, that information will need to be somewhere, but I'm not sure where it will be yet.
Okay.
Uh, oh, actually, this may be saved. I wonder if this will be done implicitly, because here's the thing. Um, oh, but that means we need to change how we do code generation, I guess. Because here's the thing. We could, I think the book is going, might do this, I'm not sure. But like a relatively easy thing to do would be to say, here, would be to say, okay, I see that E has multiple bodies, so before I start doing anything, I'm going to emit an instruction to generate a choice here before I do anything in the body, you see?
Oh, but that seems like a second, like two pass optimization stuff.
Yeah, this is going to need a, no, it's not a two-pass optimization. This is a possible, it's one possible strategy to do this because, yeah, this will need a two-pass even in multiple passes because we will need to collect all of the definitions that have the same name and derivative before we can do this.
Yeah, but well, it wouldn't be a second pass, but it's kind of similar.
Yeah, because basically you can say, okay, before, at the first thing that we do when we enter this body is set up a choice point pointing to the second body. And then here we say, okay, this is the last one, so we just have the normal body as usual. But if there was a number 3 here, well, number 2 because we're zero based,
Uh, that was
then we
very
could
Marinho.
say, yeah, then if there was a third option here, we could say, okay, in the second one, we're going to emit the same choice point creation here, except it's now going to point to this one.
Yeah,
See, the list
basically.
would be kind of implicit like that.
Yes, that's true. I wonder how we're going to identify that though before doing what you just said. Or are we going to do exactly what you just said?
uh, I don't know, actually. We need to read the book and see which instructions manipulate choice points.
Okay. Okay, we're also going to dump the current trail pointer, which is the TR register, which is needed as a boundary where to unwind the trail upon backtracking. If computation comes back to this choice point, this will be the address in the trail down to which all variables that must be reset have been recorded. This will be address in the trail down to which all variables. Okay. The current top of heap, which is needed to recover heap space of all the data structures and variables constructed during the failed attempt, which will be resulted in coming back. Yeah, this makes total sense. In summary, a choice point is allocated on the stack looking thus. Blow. Boom. A bunch of registers.
That's a lot of stuff.
Yeah. And I have another question. How are we going to know how many temporary A registers we're going to dump?
It's however many arguments the predicate takes.
Okay. Note in passing that m's choose explicit definition for allocate n must be altered in order to work for M3. This is
Huh.
because the top of the stack is now computed differently depending on whether an environment or choice point is the latest frame on the stack. Damn.
Oh, right.
Damn. Boys. Damn. Okay, let's change this then. We already have the hardware. We only need the B register.
uh, okay.
Okay, I can take a look
If E is
here.
greater than B, yeah, there's an annoying edge case here where uh, at the very beginning of the program the two are equal, right?
Well, we can add that corner case changing to a greater than or equal, no?
Uh, although I think that's probably yeah, we should do greater or equal, yes, because Although this is probably fine though, because the entry point is a query, and the last thing that the query is gonna do after setting up the argument is call a predicate. So E is going to be greater than B in that case, no matter what.
Good. But let's go. Let's change the value of new e on allocate evaluator function.
Evaluator, allocate.
Nice. Okay, so we're gonna change new e actually to 14.
Okay.
Let me actually look at the code. Are we doing everything else the same aside from the new e? So we are putting the value of e. No, go back to the code. Okay, I have the book here. So we are putting the new e on e. Yes. We are putting. We should put cp on
New E plus one.
e plus one. We should put n on new e plus two. We need
Yeah,
to
this
update
is
the e with the new e, and that's happening on 228. And we need to update the p with p plus instruction size. Yeah, so just need
yeah,
to
this
change the 214. Okay, so 216 actually. We need to put that if on 216.
not really, no. We need to do this. We need to say, okay, we need the
B
B
register,
register,
and then
and
if
then if um,
e is greater than b,
oh, actually, I don't need parentheses. This is not Zig.
yeah, e is greater
Uh,
than e. Oh, e is greater than b,
uh,
of course. Why I'm not surprised. Then
then
the answer is what is already there. Else, we're gonna have to do a new match on that
which
stuff.
is B plus stack at B plus 7.
Yeah, just copy the match and remove the plus two, essentially.
Uh, B register and no
Yes,
x plus 2, so we don't actually need the parentheses.
yes, and the answer, if there is something in there, is n plus e plus 3. No, plus 7, sorry, plus 7.
And
It's b register
wait,
plus what?
wait a second.
What?
New E is E plus stack plus 3, which is like,
It is that. Yeah, it is the same, man. Just put plus 7 on the other one.
oh right, because this N actually is,
Is the pattern matching of the E. No, of the stack. It's the lookup on the stack.
if E is greater than B, but wait, this is using the E from the E register, no?
Yes, but that's what we are doing.
Okay,
Where is
the
the
order,
confusion?
okay, no, the order is the order is flipped, that's why. So this
Plus
and this
7.
is 7.
That's it. Let's see if it compiles. Well, just do build. That's not exec because it's gonna fail. We just changed that location. Okay.
That builds.
Okay, let's go back to the book now. Nice. I am assuming this is the easy stuff.
Ligatures, they are nice.
Yep. Okay, to work
Uh,
with the foregoing choice point format, 3 new I3 instructions are added to those add already in I2. What the heck is that footnote?
this is from, yeah, it's from here.
Okay, so we actually should read that then. In David
In
Warren does not include the arity in a choice point, as we do here. He sets up things slightly different so that this number can always be quickly computed. He can do this by making B register B, and the pointer is linked in the choice point list, reference a choice point frame at its end rather than at its start, as is the case for environment frames. In other words, the register B contains the stack address immediately following the latest choice point of frame. Uh, wait, whereas register E contains the address of the first slot in the environment. Thus, the arity of the latest choice point predicate is always given by this formula, but this sucks. That's it. Nice.
Yeah, that's kind of complicated for like one cell in memory.
Okay, they are to deal with the choice point manipulation needed for multiple clause definitions. As expected, these instructions correspond respectively to 1. A first and an intermediate but not ultimate, and 3. A last clause of a definition. They are try me else, retry me else, and trust me. Damn. Okay,
That's an excellent instruction name.
that's
Just trust
Chad.
me.
Chad. Okay. So what do they do? Let's read. The try me else. Um, they have that one allocate a new choice point frame on the stack, setting its next clause field on to L on the other fields according to the current context, and set B to point to it. Having backtracked to the current choice point, well, that this one is retry me else, to reset all the necessary information from it and update its next clause field to L. And trust me, having backtracked to the current choice point to reset all the necessary information from it, then discard it by resetting B to its predecessor.
Yeah, so this basically is what I was thinking about, but the details are different because I did not consider. I forgot that we needed to reset some state,
Yeah, but
basically.
I read, but I kind of didn't get it. So allocate a new choice point frame on the stack, setting its next clause field to L, and the other fields according to the current context, and set. Okay, so this is attempt. This is basically one is basically to do an attempt.
Yeah,
True is having backtracked to the current choice to reset all the necessary information from it. Okay, so this is next. True is basically next one, and 3
is this is the last one, basically.
to reset all the necessary information. I'm not getting the difference between 2 and 3 though.
When you do a 2, you keep the choice point because there are more clauses. When you do the 3, you actually remove the choice point after
Oh,
doing
we are
the
done.
reset. Yeah.
Okay. With this setup, backtracking is effectively handled quite easy. Less famous words. All instructions in which failure may occur must ultimately test whether failure has indeed occurred. If such is the case, they must then set the instruction counter accordingly. That is, they perform the following operation. We need to implement that, so let's go.
Hmm.
This is definitely an evaluator function, for sure.
Okay, this is setting the P register.
It's a one-liner that is a pain in the ass.
Going to be added in multiple places though.
Yeah, no, we definitely should make this. You're gonna
Hmm.
receive the computer and return the computer. That's it. So yeah, you need to destruct the computer though. We're gonna need the store, and we're gonna need the B register essentially,
And then we
and that's it.
say
Just the store and the B register.
for B register.
Yeah, and then semicolon underscore. Okay, so the first thing that we gotta do is um, actually, man, copy. No, go back, go back. Copy
Where?
lines 219 to 221. Copy this. Yeah. So that's the first
Oh,
thing you're
right,
gonna do
right. Because we need to do a stack get,
on
basically.
the
We need to
using
do
the
two
B.
of them, actually.
Exactly. It's that's why I said it's a pain in the butt. This would be much easier if you had monads though. But okay. Probably there is actually a way to use the let bang that Magetta mentioned. We probably actually would be kind of nice, but not today. After you do that, you're gonna do another one, another match.
B
Oh no,
plus
that's actually
set
not needed.
B.
That's actually not needed. I'm sorry. Let's do this match a binding. Do a let addr equals this match. Then you're gonna do yeah
This is
that
not quite right though, because we need to do
it's B
B
register though
plus.
plus 4 plus n plus 4. Yep. Then
But we also need to do. Yeah, we need to do another
no, now it's gonna do a
match.
no, not another match. Now it's a stack put.
No, no, no. We need to do a match because we're going to do another
Oh
lookup
no, no,
and
you're
then we
right,
set
you're
the
right.
P
No,
register.
you're definitely right on that. My bad. Match
Match.
store stack get uh, and you need to pass the ADDR with, and then if you found an address, you're gonna return the computer with the new stuff, and you're gonna change the P register while you're at it, of course. So computer with P register equals uh, n.
Wow,
Otherwise, we just fail miserably.
amazing.
Yeah, change the unreachable those though. They are incorrect error messages.
Unreachable, backtrack. Let's call them 0 and 1. Why not?
Yeah, that's fine. Awesome. Done. Backtrack function done. Let's go back to the book now. Okay, so the following operation, as opposed to having B be unconditionally set to its follow normal course. Naturally, if no more choice point exists on the stack, this is a terminal failure and execution aborts. Eh, yeah, but we're gonna have to do the try-catch stuff. All the approximate alterations of instructions regarding this precaution are given in Appendix B. You gotta be fucking kidding me. Okay. The three choice point instructions are defined explicitly in figures 4, 1 through 3. In the definition, oh, this is the implementation of those above. No. Uh, no, but there is more code. Now we're going to talk about call. This, no, I didn't read. I didn't read. Uh, the The three choice point instructions are defined explicitly. Okay, in the definition of try-me else L, we use a global variable, num of args, given the arity of the current procedure. This variable is set by the call that we must accordingly modify for M3 for its M2 form. Uh, Global variable. Why? Do you understand this? Why do we need to hold the number of arguments in a global thing? Regardless if it's a variable or a register.
Oh, I was muted.
Well, yeah, you were all the way through.
Okay, so yeah, so basically the guy doesn't remember if he forgot to add a register or not
Which is
for
funny.
this, which is funny. And the book chose to add a global variable instead of a register because that register was never specified for the original WAM.
Yeah, but I don't. My question is, why do we need to save that information somewhere?
We need to save this information because we need to know how many registers we need to restore when we do a backtrack.
We're definitely not gonna do a global variable, so we're gonna add a new register.
We could,
Let's call it a register. To
although in this definition we use a global variable given the arity of the current procedure. Current procedure.
Yeah.
Current procedure. But doesn't the stack frame have that information already?
Yeah, that's what I think you said before when I asked that question. How are we gonna know how many a registers we need to dump? And then you said the stack is holding that info. Where?
Well, here.
Oh, so you're just gonna read the stack and immediately use that as a counter in the thingy.
That might work, but hmm. That might work, but I'm not sure if there's some caveats that we can't see yet. Um, let's actually look at the definition of the try me else instruction first. So try me else. Um, if blah blah blah, we have to decide if we're going to allocate choice, or if we have to do a lookup on the
What the
environment
fuck?
or a choice frame.
What the heck happens after that? He picks the variable, put on the stack, and use that again to put in? Why? Oh, okay. Then the reason that you need that on the stack is because you're doing the loop later. Okay, I see. Damn. Oh, the for loop is a one-liner actually. That's why it's not indented. This is a one-liner for loop. Okay. Then we do that stuff, which is kind of cute.
Uh, hmm. Okay, I think I see actually.
Okay, so why do we can't use the stack?
This needs to be a register actually,
Why?
if we're not doing a global variable, because
No, this will
when
not
we
be a
do a
global variable.
no, we need to do a register if we don't want a global variable. Because here's the thing: when we enter the body of a function or a predicate, I guess, uh, we need to know the number of arguments so we can save it in the stack to begin with to create the choice point.
But isn't it just a matter if that information is already on the stack of just copying it?
No, 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 it's not already on the stack. That's the point.
Ah. Okay, let's add the A register for arguments.
A
We have almost
register.
all
I'm
letters from the beginning of the alphabet, man.
uh okay. Machine.
And we should add comments to this madness. We should add comments on here saying like these registers for this, these registers for that. Such a missed opportunity that we had here.
Well,
Anyway,
since this register is not actually in the book, we can call it whatever we want. Why
no,
not
but I
call it arg count?
no, but I would like to call it A to be consistent with the other ones. A register. But well, we can keep it as our count. That's okay.
Uh,
That also makes a differentiation between the book stuff and our stuff.
Okay, so if we go back,
Yeah, let's continue reading the call thing. Okay, so we're gonna do this with call. Fine. As we just explained, we omit treat in the case of failure, and therefore the backtracking, where PN is not defined in this explicit definition of call. Its obvious complete form is, as those of our instructions given in Appendix B.
okay, so we'll definitely have to look at that appendix later.
Wait, they have these for all instructions?
Apparently they have, if this line is to be believed.
And we didn't check any of that. Okay.
I mean, that has the final form of everything. We are going through the book because we're stepping through those intermediate forms, you know?
Yes, but I also think that could save us from debugging some very complicated mess because we can compare our implementations.
We definitely should look at that, but
Um,
let's continue reading. Actually, let
Fine.
me first update the call instruction before we forget.
Yeah. And by the way, the call instruction was not updated to have a call stack. We are still
Uh,
one depth thingy. That's kind of funny.
CP register is P plus instruction size, which is 1, but okay. The P register is going to get updated with the address of the function, but then we also need to say arg count equals, where's
We don't
the,
have the argument here though. Go
we
back to
don't
the
have
book.
the, why do we not have the, but we should.
Go back. Wait, it is there. There is a number. There is a number there. Okay.
Oh, it's functor prime. We need to say,
Second of functor prime. But how do you do second in OCaml?
well, you can always just do this structuring, right?
Yeah, but second of tuple. Damn, can you hear the plane here?
Oh, that's a plane?
Yeah, there is a plane.
Ah, very faintly, only very faintly. I wouldn't have noticed if you didn't mention
Oh,
it.
it is second as in Haskell. Okay.
Oh,
Just do SND of functor prime. See if this compiles.
uh, this record, blah blah blah, lib machine. Did I forget to
Maybe. I don't think you did, but maybe.
machine.t is here? No, I did. It builds. Okay, that's just LSP being crazy.
Yeah. Okay, let's go back to the book. As you just explained, okay, finally the definitions of retry me else and trust me use an auxiliary, I don't know what that is,
Ancillary.
ancillary operation, unwind trail, to reset all variables since the last choice point to an unbound state. Its explicit definition can be
Yep.
nice. In
Well, but
conclusion,
that means we're close to being the final form, right?
yes, I guess there's less temporary stuff going on. In conclusion, there are three patterns of code translations for our procedure definitions in L3, depending on whether it has one true or more than true clauses. The code generated in the first case is identical to what is generated from L2 program in M2. In the second case, however, the pattern for the procedure is this. So, wait, wait a moment. Um, are we gonna do code generation for the new instructions then?
Well, we need to.
Okay, we haven't been presented with that yet, but okay, go.
Oh, okay, so basically if it has one body, we keep the way it was before. If we have two, we do try me else, then we emit the code for the first clause
And there's
with,
and there's an address for the follow-up.
yeah, but we need to know this address, right?
Yeah, that's what I don't know how
Here.
we're gonna do, to be honest.
What we can do is we remember the address of the first instruction, which we are already doing because that's in the functor table, right?
Damn, that's gonna make man, that's gonna be a mess to
We
remember.
emit the code for the second clause after that, and then we go back and fix the address here.
Oh, I see what you're doing. It's like a look ahead stuff. I see.
Yeah, we can just do a dummy value for this L to begin with, and after we know where this ends, we know the address of L, so we can just go back and fix it.
Yeah. Yeah, this is like forward declaration. That makes sense. And for the last case, go on.
And
There's
of
this is
course,
the
there's all the
code.
figures on the way.
Yeah.
Okay, for the last case, we do a try
Ooh.
me else.
Oh, they just
Okay,
call each other. Okay.
okay. But
That's
yeah, but this does imply that we actually do need to collect all the definitions of a given predicate before we actually emit any code.
yeah, but that's who is going to do that? Are we gonna do like make the parser? Remember?
Uh, well, the easy thing to do would be actually to define the AST in such a way that we must put an OR at the top level of at the outermost layer of a predicate, if there is an OR, if there are multiple clauses. And then the hmm,
I don't think that's the easiest way, man. I think the easiest way is to pick whatever the parser produced and fold that before giving it to the compiler. And the
yeah,
fold does the accumulation and the aggregation, let's say.
yeah, that's actually probably easier.
Yeah, it's more inefficient, but it's easier for sure. And right now, I don't really care about efficiency. I'm curious about the code generation of those things. We haven't been presented with those again still.
But we have, this is the case to handle multiple clauses. This is how we handle
No, yeah, but what is the code that's going to be generated when you say try me and else?
that's the new instruction. It's literally this instruction.
Oh, so this is just an instruction that has a number.
Yeah,
Okay. Damn. So for example, M3 code definition for the code definition is given. Wait,
in figure.
is this the generated code? Go on. Keep scrolling.
Yeah, the generated code is here apparently.
Damn. Perfect. So we can actually use this to check our implementation. What after that?
Mm, that's actually the end of the chapter.
Damn. Okay, this was very productive. Um, okay, I think we can start by adding all of the try me else, retry me else, and trust me um um, cells.
Instructions.
Yeah, go to machine.ml. Well, you can commit this already if you want. Well, don't
Yeah,
forget to format it.
actually, I think I'm gonna do that. Dune FMT, nothing changed. So here and here, uh, add L3 registers, and then this can go back to being like this. And then we say prepare existing. Well, actually, we're not doing that for everything technically. Prepare for backtracking implementation. And we should change the L3 example. Actually, let's make two examples for L3. Why not?
Sure.
L3 code gen, because I want to have uh, this program there
Okay, I
actually.
can I can dictate it to you, so then you don't have to copy paste. So it
Okay.
is P XA, yeah. Then it's
Oh,
PBX.
P
No,
B
the non-capital B.
X
And then it's PXY. Well, I just said I would dictate it to you, but okay. And then body here. PXA again, the same as before, comma. No,
X
XA,
comma
yeah,
A,
comma again.
and then
PBY. And non-capital B and Y. Dot. Yeah, that's it. You need a query though.
we need a query. Well,
Well,
actually,
actually,
no,
not
this is just
really.
for code gen.
Yeah,
Yeah.
this is just for CodeGen. Ah, nice. Ah, this is progress. I'm kind of surprised I am understanding stuff.
Uh, okay. Uh, let's see. We need to do.
What do you want to do first, though? Do you want to implement the evaluation functions, or do you want to do the code generation first?
I think we should add the functions first, like the three instruction implementations.
Okay, let's do that. We have 45 minutes. Let's see, how far can we go? Did you commit?
Uh, I did, and let me actually push before I forget.
Nice. Okay, so which one do you want to do first?
Let's follow the order of the book, I guess.
So try me and else first then. Well, you're gonna receive a
Uh,
computer and return a computer. Oh, and a number. You're gonna receive a number and a computer.
all right.
The name of the
So
number should be L.
try
Try me.
me else,
Yep.
and it receives an L.
Which is an integer, and a computer, and we also have to destruct the computer already. Let me tell you what we're gonna need. We're gonna need a store, E register, B register. Actually, all the registers.
All of them.
Yeah. Yeah, all of them.
All of them. Okay.
Yeah. So I can list them to you. Break the line, man. I think it's gonna be horrendous if you don't break the line. CP register,
Uh,
CP register, H register, TR register, um, P register, and I think that's it for the registers. You also need the store, and we also going to need the args count, and that's it actually.
we don't have a TR register. What do you mean?
I think LSP is just going insane.
Okay, it builds. Yeah, that's just LSP being crazy.
Yeah, which is kind of rare. This is the first time that it's actually get being wrong a lot of the time. But okay.
Is it
Uh,
really?
yeah, with me it works fine. It updates after Doom stuff. Okay, let's go then. The first thing we're gonna do, we're gonna do the copy. No, no, no. Go back. The copy line. Where did we do the if? Yeah, copy this. All of this. No, it's not. I don't know if it's going to be exactly the same, but we need this.
Yeah, it's not quite the same.
Yeah, but just copy it. No, no, no. From the let. We also need the let. But it's not going to be new E. It's going to be new B. Yeah. So place new B instead of new E, and then we check if E is greater than B, which we are doing. Then we do a stack E plus true. If it's there, we do that plus E register plus 3. That's correct. Else, we do a stack get on the B register plus B plus 7. Yeah, this is exactly what this is exactly what we need. Okay, let's continue. Uh, the next thing on the book we're not gonna do. We're just gonna do this when we do the computer. Actually, that's not true. Okay. Okay. Let's do a bunch of pipes now. So this is gonna be store.put stack put in this case. I don't remember the arguments, but we need gonna it's the
Fix an A, an address,
and a
and a
compute
store.
and a store. So the A is the value, I assume. Yeah.
Uh,
So the address is gonna be new B. Oh, the value comes
uh,
first, so it's arg count. No, 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 arg count first.
arg count, but actually we can't just do an arg count because this needs to be a valid cell. So cell dot
Parentheses.
address. It needs to
Yeah,
be in
but this is not an
parentheses.
address though. This is just a number of arguments.
Uh, jump to definition failed.
Yeah, you need to do machine.cell.address. No,
Still
LSP is still
failed.
not working. Well, but it sells stuff.
But is it perfect?
I'm not gonna explain that. I'm gonna let the viewers, whoever is watching this, try to understand the reference. Yeah.
I think we're using address whenever we need to store a raw integer in there.
Maybe we should add a new tag here, just for like arg count. I don't know. Because we're kind
Mm,
of overloading address. Like there's nothing of address in this number.
okay.
Yep. So then you're gonna do arg count. Then pipe, continue the pipe because now we're gonna do. Then we're gonna do. We're not gonna implement this, but now is the for loop. I suggest we make a function, a separate function, auxiliary function, just for the arguments, just for the registers, the A registers. You know what I mean?
This for
We
the
check.
A right, because we need to grab, yeah, we need to grab all
Yeah, which
the.
reminds me, we need to grab the registers from the computer. We didn't do that. I forgot. Yeah. So put whatever like aux reg register aux space registers. I don't know X registers and the new
Uh, we
B.
need to, we need to know the
We need to receive the store and the new B in the registers. That's it.
store, the new B, and the
And the store
registers.
needs to be at the last argument to for the pipe. Save
Okay,
registers.
let's
Just call it
save
save registers.
arguments actually.
Yeah. And new B, and that's it actually because now it's the store. And we're gonna do the store
Uh,
via the pipe.
and we need the X registers as well.
Oh, that's true. Okay, let's keep going with the pipe. Now let's do all these literal ones after the four.
Okay, those are all just star puts, right?
Yeah,
Stack puts.
yeah. Just make six. Yeah, six times this. Okay. Uh,
New b plus n plus 1 plus 2, 3, 4, 5, 6. Okay.
all of these will become addresses. So replace all the arc counts in this block for addresses. And then what's going to change is the plus. So uh, select all of these and do new b plus n as well.
E register. This is the CP register. Oh, not copy sign CP register.
No, 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 that's not correct, dude.
Why not?
Wait, wait. Oh no, it is correct. The new b stuff is later. Okay, now continue. B, then L, then
L. Do we have
tr.
an L register? Oh
Yes,
no, L is actually
the argument.
the argument. Okay.
Yeah, then we have the tr register and then the h register. And each will update the new b's as well. So it's gonna be new b plus one plus n. We need to do the let to get the n first. We forgot. I thought we could do this later, but we can't. So before 232, let's do a let binding there.
But n is just the value of the thing at
Yeah.
new b, which is just the register count actually. Well, the arg count.
Oh, okay. So let's use that instead then. So it's gonna be new b plus n plus that plus arc count plus a number that's gonna change from line to line, starting from 1 and going all the way to 6.
4, oops, 5, and
Could
6,
you
and so many
align the
lines.
new b's like with spaces so they are like, yeah, nice. Okay. After we do this though, that's all of let's do another pipe. Let's do another pipe and let's actually return the computer because with the new stuff. So you need to do a lambda now. Pipe lambda, do a fun to get the store. Uh, yeah, so and then I don't I forgot the syntax again. No, it's not like that.
Um,
It's definitely not like that. I think it's arrow. So fun store arrow, single arrow, and then it's computer with, and then let's start. So the B register is equal to new B. Then the HB register is equal to H. You can format this already, by the way. And the P register is equal to P plus the instruction size. No, P register. You need to repeat that. Nice. And this and with store as well. Semicolon store. Close this. Format. That's it. Now we need to
so
implement save
actually, this
arguments.
needs, yeah, this needs to be here actually.
Yeah. And now save arguments implementation. So we have to.
Okay,
Okay, no, I was about to propose. Are we gonna do this outside of try me else? Because this seems like a function that only makes sense for try me else.
but we need to save the arguments. Do we need to save the arguments in retry me?
No,
We
no, we it's a different operation. And trust me, let's check trust me as well.
we do actually.
No, this is not the same as what we're doing there. This is the
It is.
opposite of what we're doing.
No, 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 no. It's. Oh, okay. No, actually, yes, you are correct.
Yeah, so I would say make save arguments inside the try me else function as a separate internal auxiliary function. It can be before 226.
Okay.
So let
Let
save
save
arguments.
arguments. You need to take
You need to take whatever you wrote there. So the new b, which is a number, so an integer.
uh actually, can we do this later and then we don't have to pass the new b explicitly as a parameter?
What do you mean? Oh, you want to make this after the new b, so then you don't have to pass those as arguments. I
Yeah.
see. Okay, I am okay with that. You can remove both of them, but put this after yes. So you receive the store and return the store essentially. Yeah.
Yeah, we
Now we need to do a folder function. So let folder, and that's going to receive the accumulator and an index, essentially.
the
You're looking
accumulator
to
and
the
an
wrong.
index.
You're looking at the wrong one, by the way.
Uh, there we go.
There it is.
Man, it just sucks that this is all one based.
Well, it doesn't matter. So let's do the folding function, which is going to receive the accumulator, which is going to be the store, and an index. So let folder. I don't remember the order of the arguments, but this doesn't matter. Let's put index and acc, or whatever the order you prefer. And then let's do stack store store get. No, stack get. This store is the opposite, Marin. We are tired. No, no, no. It's a store dot stack get. No, not that. Stack get is a function. No, we are close to finish though. I'm also tired. You're gonna pass the address first, right? What is the order? I can't hear you, Marin. By the way.
Uh, we take the store, then the address, then we turn an A.
Okay, so ACC. The address is b plus I, the index.
ACC. Um,
Wait, I'm looking at the wrong one again. Ah. Oh, actually, it's a stack put. My bad. It's a stack put, man.
yeah, it's a stack put.
Yeah. What is the order
Uh,
of stuff?
well, stack put
Oh,
takes
the
the
value
value,
first.
the address, and then the store.
Okay, so do put x, x space acc. We're gonna replace the x later with something else. Uh, no, not that x. We're gonna do a let. It's yeah, acc. Then what else is on the put? Oh, now comes the address. Okay, the address is new b plus index after the x. In parentheses, by the way. Plus index. ACC. Um, and that's it. Now we need to do the x. So do another let before the stack put.
The X is going to
The
be
value of the register. The value
of the
of the A
register.
registers. We're going to do a lookup using the index.
Let's call it
Yeah,
argument
yeah, but
and
we need to do
let.
an open though. Um, Search on this file where we're using the X registers.
Okay.
At some point we're doing a lookup with them. Uh-huh. Continue. Continue on the grep. This is adding, not finding. This is okay. Still not
Open
that.
machine int
There
map.
it is. No, 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 but copy the find as well. Yeah, these two lines we need them. There it is. Yeah, so open, we do the open. Then we do the find, but instead of index of register, it's gonna be index of the folder. Okay, format all of this shit.
Um, Expecting expression, right? Because we need this for it to be
Okay.
syntactically
Now
valid.
instead of the unit, let's do the fold left.
Uh,
No, it's least. Wait, we don't have. What are we folding? That's actually a good question.
can't we just do a for loop? We can't because that's side effectful, right?
Okay, I lived to hear Marinho propose a non-functional, mutable way of doing things. Okay.
The
I
problem is that a for loop is actually it doesn't return, right? It's not like closures because closure for is actually list comprehension, not an actual for loop.
Yeah, but Haskell's for is also not this for. But that's why I'm proposing to do a fold.
Mm,
We need to do a fold.
a fold is fine. The problem is that we need to allocate a list of numbers just to traverse them. That's annoying.
Yeah, that's what I was about to say. What are we folding on? Um, what are we folding?
Well, we need to fold from using a range
Oh,
from
it's a
0
range.
to.
Okay, no, actually this is fine. OCaml has ranges in lists.
Oh, okay.
We know the range. It's n as well, by the way. Which, by the way, do we have the binding that I mentioned about the n? Oh, it's arg count, the n.
It's the arg count, yes.
Okay, so range. How do we do ranges? So list range OCaml. Module list. You gotta be fucking kidding me. Create list with range OCaml. Thank you, Stack Overflow. You gotta be. Oh man, you have to write it yourself. Okay, that's a little bit annoying, but fine. Okay,
Why
so
do we still expect any different from a camel?
okay, so I copied the solution in the chat. Just paste that. Ah, fucking damn it. Oh wait, there is a solution with batteries that's better. Okay, it's list dot ofenum. You need batteries to this, and then instead of doing all of this shit, you do open parentheses. There is extra syntax. Okay, uh, 0 dash dash arg count, and I don't think you can put spaces. I think they need to be glued. Yeah, let's see what happens with this.
Yeah, the formatter actually added back the spaces.
Yeah, but the guy here is saying. Okay, let's see if this compiles though, because this was not on the yeah
Oh, we need to
folder.
do the we need to
Yeah,
actually do the
list dot
fold.
fold left folder and then this thing. It's list dot fold left, by the way. Yeah. Let's yeah, what is the order of the arguments? Yeah, it's ACC, then index, then oh, we need the initial accumulator. No, it's a pair. We need to make it a pair.
Why?
We need to make it a pair because never mind. Let's go. Try to build this.
It builds.
Damn. Damn. We are very good today. First try everything. Okay. So we have 20 minutes left. Do you want to try the other function?
Huh, that actually okay.
That's kind of surprising that this worked. I'm still a little bit. Oh, okay. So do and build doesn't mean anything. Nice. Thanks, OCaml. 96 on machine. Let's go there. Is there a trail size?
I think the trail starts, if I'm not
Yeah, you need
mistaken.
to put it there. 43 and stuff. You need to define the size of the trail, essentially. No, what is the trail start actually?
Either the PDL or the trail start after the stack, and the other one actually starts at the end of memory and grows backward.
Yeah, but it's saying that it doesn't find it. So go to machine.ml, well, store.ml, and let's see if there's a trail start available here. And the answer
There
is no.
isn't.
Okay, so that's
There
why it's
isn't.
broken. So put on the signature and then put in the implementation as well. The signature is up there, Marin.
Okay.
Trail start. And you need to define what the heck is it. Go to PDL start and then let's copy paste from there. There it is. So what is going to be the trail start? They need to start from the opposite directions, no?
Well, it's just the PDL start plus the PDL size,
Trail size. Yep. Okay. Compile time again. Damn. Uh, I have a suggestion. So
We
instead
need
of
to
list,
do.
yeah, I need to do let open. We need to open the batteries. The problem is that if you do that, the list.fold is not. I think is gonna break. But it's batteries list. I think dot list maybe. I don't know how this works. Let's try this. See what happens.
Oh, okay. So actually, we can do batteries dot list of enum, right?
Yeah, that's what I'm thinking. But again, let's
But
see.
then this is actually unbound.
We're gonna have to do batteries dot list dot. Amazing. Let's just do the open and see what happens, man. Ah, damn.
There we
Maybe that
go.
you need parentheses in those. I don't know. No, in both. Parentheses in both even. I'm a little
But
bit skeptical that
then
it's going to work, but okay.
that
Let
yeah
me.
that doesn't look right. That does not look
Yeah,
right.
but let's see if it is just LSP being fucked up. I'm actually gonna look in batteries to see if there is list stuff in there. Let's see what happens with this.
Unbound
Ooh,
value.
but the off enum worked. Try to remove the spaces.
But the spaces don't matter actually.
Well, we don't know that.
We do because the formatter actually added the spaces.
Uh, okay, let's see if batteries. What the heck? Batteries. Wait. The autocomplete was showing the thing. Go back. Batteries dot what? Ooh. Okay. Can we keep this? Well,
Can
can
we
you
just
save
say
and try
let
this
open
out?
batteries? Actually, we can.
Unreachable get structure. Okay, this actually makes sense. But remove the 242 then. Does this work?
Well, I need to add the list back here, but it should. Yeah,
Nice. Boys, we did it. Okay, so we have what, 17, 15 minutes. Do you want to try the other function?
we should commit this first,
Yeah,
no?
definitely commit. But this looks awesome. Look at that. Just look at it. Look at those pipes, man.
Yeah, concatenative programming for the win. Well, it's not really concatenative because we
Yeah, but
have.
I'm really proud. I'm really proud of this.
Uh, okay. Implement try me else instruction.
Well, I would change that commit message to evolve, but okay. Okay, next one. What do you want to try? Retry me else or trust me?
Actually, before we do that, we should probably add the instructions to the
To the machine. Yeah, let's do that.
machine definition. Yes.
Yeah, so let's add all three of them. So trust me else, try me else, and that needs to receive an int. Then we have retry me else, which also receives an int. And trust me actually doesn't receive anything. Okay, let's go. You can commit this already also. Machine cell def. Well, it's done.
Well, we can amend the message.
Machine cells definition. Nice. Okay, so your call. We have 14 minutes. Do you want to try another one or we finish early? Your call.
I wanna finish early actually because I wanna eat something.
Yeah, okay. So I'm gonna finish the recording. So,
I think we made good progress.
no, today was great.